So welcome to the first Fluids and MHD seminar of our semester 2. So today we've got Daniel Lecoanet from Northwestern University. So he did his PhD in Berkeley and then had postdoctoral fellowships in Princeton before moving to Northwestern, online back in September. And I think he's still in NYC, but working at Northwestern as an assistant professor. And he'll be talking today on work in astrophysical fluid dynamics on wave conversion from stellar magnetic fields. If you'd like to go ahead, I'll switch off my camera so people don't see me.
Okay, thanks for the introduction, Adrian, and also the invitation to talk about this work. Yeah, so as you said, I'm going to be discussing how we can learn about magnetic fields deep inside of stars by studying waves. So first, I just want to start with this quote that I like by Arthur Eddington, a very famous and very productive astrophysicist. So in 1926, Eddington wrote that he thought the deep interior of stars is less accessible than any other region of the universe. And although this might have seemed to be true in 1926, we now know quite a lot about the deep interiors of stars. And that's because if you look at their surface, so this is a movie of some observations of the surface of the sun. There are fluctuations at the surface, and you can use those fluctuations to back out what the interior structure is. So the idea is that a star like the sun is organized as follows. The inner part of the star, well, the real inner part, like in the deep core, you have nuclear reactions which generate energy, and that energy has to leak out of the star. It has to leave the star for it to be in thermal equilibrium, and for the first 2/3 of the star by radius, the energy is transported just by photon diffusion. So just photons bouncing around in the opaque plasma is able to transport the heat. But as you move outwards, the properties of the plasma change, and photon diffusion can no longer transport the heat that's being generated by the nuclear reactions. And instead, that energy is in part transported by bulk fluid motions via convection. So the interesting thing is that if you look at the surface of the sun and you measure brightness fluctuations, and you plot those brightness fluctuations as a function of their frequency and their spherical harmonic wave number L, you end up with a diagram that looks like this, where red corresponds to large power and blue corresponds to small power. So you can see that there's these distinct patterns here where you have a large power in these ridges, and these correspond to the global oscillation modes of the sun. So it turns out if you looked at the sun, and paid close attention, well, I guess you would probably burn your eyes out. But if you had like some nice sunglasses so that you didn't burn your eyes, you would notice that the sun, the sun actually, the overall brightness fluctuates on about a 5-minute time scale. So about every 5 minutes, the sun's brightness will go from a bit dimmer to a bit brighter, back to a bit dimmer. And it turns out that 5-minute time scale is the largest amplitude waves that are bouncing around in the sun, whereas there's a whole host of other waves, as you can see in this diagram. So basically for each value of L, we can measure little peaks, which you see as these ridges in this diagram. And those each correspond to oscillation modes. And at this stage, there have been thousands, 10,000, maybe even hundreds of thousands of modes observed in the sun. And those sound waves are being excited by that convection, which is happening near the surface. So, so the presence of these modes allows us to do what's called heliosismology. I mean, this is, of course, first done in the Earth, where it's just called seismology or like geoseismology. An earthquake goes off, and then that generates waves. And by measuring the properties of those waves, you learn about how the structure of the Earth, because the structure determines the wave propagation characteristics. So for the sun, it's a little bit different. There aren't earthquakes. It's just kind of some constant generation of waves by the persistent convection. And the way that you try to understand the structure of the sun is that you first make a guess of what, say, like the density, pressure, temperature, all those quantities are as a function of depth in the sun. So that's what's being plotted here. So here you can see that you make some guess. You say that maybe the density goes between 10 to the minus 8 to 10 to the minus 4 grams per cubic centimeter from a little bit above the surface of the sun, which is 0, down to about 5 megameters, which is the preferred length scale of solar physicists. Once you make this ansatz for what the density is and all the other properties, then you can ask what are the types of oscillations that exist for that state. So you basically just solve an eigenvalue problem. You get a bunch of different eigenvalues. So here I'm plotting different. I guess these are velocity profiles associated with different types of modes near the surface of the sun. And each of these has a different frequency. And you can compare those frequencies to the frequencies that are actually observed to see if your density profile is correct or not. And then if there's some difference, then you can modify your background profile until you get a nice fit. So that's what's called heliosismology. So now I just want to kind of make like a census of what are the types of waves that we could use to try to understand the properties of stars. So the first one that I'm going to talk about are the internal gravity waves. And these are going to be especially important for the rest of my talk. So I'm going to try to go into this in a bit of depth for those of you who are not familiar with these. Internal gravity waves are waves that exist in media which are stably stratified, which is to say that the density gradient is negative. So this is an example. So here I'm plotting some background stratification. So as a function of height, I'm plotting the density. You can see that low down you have a high density, and high up you have a low density, and that's stable because you have the lighter stuff on top of the heavier stuff. If it was the other way around, where you had heavy on top of light, that's unstable to convection. Okay, but here we're looking at a region which is stably stratified, and imagine you take a fluid parcel in the middle of the domain and you displace it downwards. Okay, so now it's here, but the density that it has is different from the density of its surroundings, which is given by this line. And you can see that in particular, it's going to be lighter than its surroundings. Because of that, there's going to be a buoyancy force upwards. So this displaced fluid parcel is going to start moving upwards. It's going to rise, and it'll overshoot its original position and end up too high. So now it's up here. Now if we compare the density of the fluid parcel to its surroundings, which is here, it is denser than its surroundings. So there's a buoyancy force downwards, and it's going to fall and undergo these types of vertical oscillations. So that's what these internal gravity waves are. It's oscillations. The restoring force is gravity. And because of this, in astrophysics, sometimes these are called G modes because the restoring force is gravity. Okay. It's relatively straightforward to do a simple analysis of how fast you think these types of oscillations would go. You're going to get a frequency which is related to the strength of gravity and the density gradient. Recall a d rho dz here is negative, so this whole quantity would be positive. And this combination of parameters is known as the buoyancy frequency, or also sometimes called the Brunt-Väisälä frequency. So the thing to remember about these internal gravity waves is that they're only associated with vertical motions, or if you were in spherical geometry, they would only be associated with radial motions. So, so as I mentioned, for purely vertical or radial motions, the frequency of oscillation is equal to the buoyancy frequency. If you had a horizontal displacement, then there's no gravity restoring force. So there's actually no oscillation associated with that. So the frequency of that will be 0. And if, in general, if you have motions that are at some angle with respect to the vertical, then what you find is that the frequency is given by the buoyancy frequency times the cosine of that angle. So this is something that just smoothly goes between 1 for vertical oscillations and 0 for the horizontal oscillations. And I mean, of course, this is what you get by just like solving the dispersion relation, but you can think of it as just kind of interpolating between those two limits. So something that I'm going to talk about next is writing this in terms of the wave vector. So recall that if you have waves, you have a wave vector which tells you the direction that the phase is changing in. So if you have vertical oscillations, the lines of constant phase are vertical, so the phase is changing in the horizontal direction. So this type of motion has a horizontal wave vector, whereas horizontal motion has a vertical wave vector. And here it's somewhere in between. Okay, so so you can rewrite that cosine theta in terms of the wave vector, and this is what you get. You find that the frequency is given by the buoyancy frequency times the horizontal component of the wave vector squared over the total component, the total wave vector squared. Okay, so just to think about the limits, if kz is equal to 0, which is to say that the wave vector is purely horizontal, that's a vertical oscillation, then we get omega equals n as before. Okay, and there is a very important property of internal gravity waves, which will be important for the rest of the talk, which is that the phase velocity, which is the direction of the wave vector k, is perpendicular to the group velocity, which is d omega dk. That's the direction that the energy propagates in. Okay, so what does this mean? Well, if you have oscillations in this direction, so that means your wave vector is in this direction. That means that the energy, or like a wave packet, actually propagates in this direction. So the propagation direction is perpendicular to the wave vector. And in particular, if you have a wave packet which is propagating upwards, its wave vector is downwards. And you can actually prove this in a pretty straightforward way. The only dimensionful quantity that the internal gravity wave knows about is the buoyancy frequency. So that means that the form of the dispersion relationship has to be as shown here, that the frequency of the wave is given by the buoyancy frequency times some function of only the direction of the wave vector. It can't depend on the magnitude, only the direction. So if you take a derivative of omega with respect to the wave vector, then that is going to be proportional to this quantity here, the derivative of the direction of the wave vector with respect to the wave vector. And if you work out what that is, it turns out that it's proportional to this tensor here, the identity tensor minus k over k squared. And now if you take this tensor and dot that with k, you're going to get 0. So so that's saying that this group velocity is perpendicular to the phase velocity, and that's a general property of waves that only know about a frequency. Okay, so I'll just repeat this again. The group velocity is perpendicular to the phase velocity for waves, and this is in some sense like the most important point of the talk. So if you knew nothing about internal gravity waves, I hope you take this away. The group velocity is perpendicular to the phase velocity. You can now go to sleep. Okay, so you've already gotten the main point. Okay, so that's what I wanted to say about internal gravity waves. There's also pressure waves, sound waves. So these are what are actually seen in the sun, and the important thing about these sound waves is that there's a sound speed, and in a spherical medium, sound waves care about this what's called the Lamb frequency, which is equal to the sound speed over r, and then there's a constant proportionality that has to do with if you do like a spherical harmonic decomposition, this is the spherical harmonic degree L, and it turns out that that in order to have a sound wave, you need to have a frequency which is larger than both this Lamb frequency and the buoyancy frequency. So in this, so here I'm showing for a red giant star, which is what I'm going to be talking about. The buoyancy frequency n in red as a function of radius in the star, and this Lamb frequency blue in blue. So in this region up here, so for these radii and frequencies, you get sound waves, whereas down here you get internal gravity waves. And what's interesting is that if you pick kind of like an intermediate frequency, you can see that you have waves which so you can have a mode which looks like a sound wave in the outer part of the star. So for a radius greater than say like a 0.01 of the stellar radius, but then for the inner 1% of the star, it's going to act like an internal gravity wave. And it turns out that there's an evanescent region in between, but for this type of star, it's actually very thin. So these waves are waves that have been observed at the surface of these stars, and people are very interested in them. And then the last thing that I want to mention is magnetic waves. So if you have an ionized gas, as you have in stars, they support magnetic waves, and so there's kind of some classification of waves. I'm specifically interested in the case where the sound speed is much larger than the alphane velocity, which is some velocity scale associated with the magnetic field strength. So this is just proportional to the magnetic field strength. And in that limit, the fast waves look just like sound waves. So they have this dispersion relationship here. And then you get these two types of waves, slow magnetosonic waves and alphane waves, which have this dispersion relation here. And these are kind of like, you can think about the magnetic field lines as being like strings that have some tension associated with them. So you have a Lorentz force which provides tension along these magnetic field lines, and you can pluck the magnetic field lines and get waves, which are just like waves on a string kind of. And they have a dispersion relationship that looks like this. In particular, for these waves, the group and phase velocity are aligned with each other. Okay, so what types of waves have actually been observed? Well, I mentioned how in the sun, many types of waves have been observed, or many waves are observed, but the only types really that have been observed are these sound waves. And that's because in the sun, you have convection in the outer part of the sun that's exciting sound waves. It would also excite, people think that it also excites these internal gravity waves, but those internal gravity waves, they only live in the core of the sun, so they don't really make it out to the surface. People are very interested in trying to measure the properties of gravity waves in the sun, but it has so far proven to be relatively elusive. But we can find other types of waves by looking at different types of stars. So this is something that has only been possible in the past 10, 15 years because there have been different types of satellites that have been put into space, including CoRoT and the Kepler satellite. So these are satellites that go into space and they look very precisely at stars to measure very precisely how much light is coming from the star. And one reason for doing this is that if there was a planet that was every once in a while passing between you and the star, it would periodically make the star look dimmer. But in addition to that, you can also measure these types of oscillation modes in the star. So the way that I like to think about it is that the real purpose of these telescopes is to study the stars, do so-called astroseismology, where we're learning about the interior structure of these stars. And every once in a while, they might find a planet orbiting another star, but I think that's kind of boring. So I'm just going to focus on the stars themselves. So this is the type of data that you might get from the Kepler telescope. So each of these panels shows a different star, and in black I show the brightness of the star. You can see that there are some very regular oscillations, and then if you take a Fourier transform of that, so that's shown in red, you can see that there are lots of peaks, and those peaks correspond to the oscillation modes, the global oscillation modes of that star. Now, unfortunately, these other stars, we can't spatially resolve them. So for the sun, we were able to show these ridges where for different spherical harmonic degrees, there were certain frequencies that had more or less power. But here you only get the disk average. Okay, so there's one last piece of background that I want to mention, which is a specific type of star, a red giant star. So most stars, they spend the beginning parts of their lives. They have they're mostly hydrogen, and they burn hydrogen into helium in their cores, and that's called the main sequence. But eventually, they run out of hydrogen in their core, and then so they have helium in their core. They have hydrogen in the envelope. The core is going to contract, but it turns out that the rest of the star kind of heats up as well, and eventually you can start burning hydrogen in the envelope. And when that happens, the envelopes of these stars become convective and they puff up, and that gives you a red giant branch star, or an RGB star. So so people have tried doing this astroseismology for these RGB stars, and they get frequency spectra that look like this. So you can see all these nice oscillation modes. But the perplexing thing was that it was found that there are certain pairs of stars, so this star here and this star here, where almost all the peaks line up. Okay, so if you look at like this black peak, this blue peak, the frequencies of those line up, and that tells you that you think that these two stars are the same type of star. They have the same mass, they have the same, they're at the same stage of evolution. But the perplexing thing is that if you look at the red curve, these red peaks are much smaller in this one than in this one. So even though looking at the other ones, we thought that it was the same type of star, there's something that's subtly different between these two stars that changes the amplitude of these peaks. And via some complicated analysis, it has been determined that these ones are specifically the L equals 0, or excuse me, L equals 1, or otherwise known as the dipole modes. And in general, they found that there were lots of types of stars where you could find these pairs where you think that the stars are the same type of star, except one has strong L equals 1 modes and the other one doesn't. So the question was why? So and the hypothesis I'm going to tell you about is that we think that the stars which had small L equals 1 modes have a strong core magnetic field. And one of the reasons for this is that you can look at the proportion of stars that have these suppressed dipole modes, and you can see that that gets pretty large, up to 50% for massive stars, stars with mass between like 1.5 and 2 solar masses. But then for smaller stars like the sun, this hardly ever happened. And there's something very important that happens in the story of stellar evolution between these lower mass stars and these higher mass stars, which these higher mass stars, when they were burning hydrogen in their cores, they had convective cores. And we think that convection is a good way to generate magnetic fields. So you think that these stars probably have a strong core magnetic field. Whereas stars like the sun, they have convection only in the envelope. They don't have any convection in the core. And because of that, we think that those stars probably don't have a strong core magnetic field. So this is kind of maybe a natural explanation that maybe some of these higher mass stars have strong core magnetic fields, and that's messing up some of these waves and preventing you from seeing the waves at the surface. If that was true, it'd be very exciting. It would be a way to determine these core magnetic field strength by just looking at what's going on at the surface of these stars. So this is kind of like just a schematic description of this hypothesis. These red giant stars, they have convection in the exterior that generates sound waves. But those sound waves, as they propagate inwards, they actually convert into internal gravity waves. And then if there was a strong magnetic field, then those internal gravity waves interact with the magnetic field in some way that prevents them from ever making it out to the surface. If there was not any strong core magnetic field, then they would bounce off the center, make it back to the surface, and be able to set up global standing modes as these so-called mixed modes. So that's kind of the picture. And this basically this is only going to happen for these more massive stars. Okay, but then the big question is, well, how could these internal gravity waves interact with the magnetic field in a way that would prevent them from making it back up to the surface? So that's the problem that I tried to study, and that's what I'm going to describe in the rest of the talk. So this is the simplified setup that I used to study this problem. So I've simplified a lot of things. Instead of looking at a star, I'm just going to look at a Cartesian box, which is going to be could maybe imagine that's like a local segment of the star. Although an important thing to remember is that we're talking about these dipole modes, L equals 1. These are modes that they're actually global in the angular directions. So I guess maybe a better way to think about this would be that you took like an annular section of a star, and you kind of changed the geometry. You kind of folded it on itself so that it looks Cartesian, just to simplify the calculation. And I'm just going to be solving the linearized Navier-Stokes equations with this a density perturbation term. So here I have my buoyancy frequency squared. And then there's also going to be this Lorentz force. So this is like this tension force that you get from the magnetic field, and the induction equation, which tells you how the magnetic field is generated by fluctuations in the velocity. Okay, so these are the equations that I'm solving, and kind of the way that I'm going to set up these simulations is that I have this box, I have damping layers at the top and bottom, and then I'm going to drive waves at the top, and the waves that I'm going to drive are going to be these internal gravity waves. I'm not so interested in the fact that in the star you have sound waves, which then convert into internal gravity waves and then go into the core. That conversion process, I think, is pretty well understood. So I'm going to skip that. I'm just going to look at when the waves are already internal gravity waves. So I'm going to drive waves. They're going to propagate downwards, and then there's going to be some change in the background properties, either a change in the buoyancy frequency or a change in the magnetic field, which is going to cause the wave to interact with the magnetic field more strongly down here. And then we're going to see what happens. So in particular, when I drive the waves, I pick both the horizontal wave number of the waves and also the frequency. So there's going to be two cases that I do. So this is kind of like an outline of the remainder of my talk. First is going to have a constant magnetic field with a variable buoyancy frequency, and then the other one is a variable magnetic field with a constant buoyancy frequency. These simulations are done using Daedalus, which is a pseudospectral code that I've helped to develop. It can solve a wide range of equations that you specify as using strings. So it's very easy to solve different types of equations. I mean, I normally use it to study convection or other problems with like nonlinear problems, but here easy to modify to just solve this linear equation. I just want to mention some of the other Daedalus developers, in particular Keaton Burns, who is a postdoc at MIT, who wrote most of the code, and Jeff Vassell, who's at University of Sydney, who developed a lot of the algorithms that we use. So this is what the simulation looks like. So let's see. So I'm driving waves up here. These are these internal gravity waves. If you look at this region here, it might look like the waves are going upwards, but really the waves are going downwards. That's because what your eye picks out is the phase velocity of the waves. And because the energy is going downwards, that means that the group velocity is downwards, so the phase velocity is upwards. In the upper part of the domain, we have waves that are propagating upwards because of the way that I drove them, but I have a damping region, so we don't have to worry about them. Now, the waves that went down, you can see that there's some specific height where they actually stop going down, okay? And instead, now we start to see some sort of pattern which develops up here, and basically, so that this is kind of the question. It's like, well, what's going on in this region here in this simulation? Why did the waves stop going downwards? And this has to do with how they're interacting with the magnetic field. So, if you take the linearized wave equations or the linearized Navier-Stokes equations, you can rewrite everything in terms of an equation for just a single variable, the vertical velocity, which I'm going to write W. And here, so here we have the magnetic field, which is assumed to be constant. And I think here I assumed that the magnetic field was vertical. So it's actually very important to have a vertical component of the magnetic field. It doesn't have to be purely vertical, but if it's horizontal, the problem is qualitatively very different. Okay, and then so this is supposed to be constant, and then the buoyancy frequency in this problem is a function of height. So you can see that if the buoyancy frequency was 0, then you can remove the Laplacian from this term and this term, and you're left with a dispersion relation of the magnetic waves. In this case, because it's 2D, it's slow magneto-sonic waves. If the magnetic field was 0, then you can neglect this term, and then these two terms give you the dispersion relationship of the internal gravity waves. So what we're interested in here is that the fact that this buoyancy frequency has a slow vertical variation. So we're going to say that it's varying on a large vertical length scale, capital Z, and then there's going to be a small vertical length scale, little z, we're going to solve this problem using multi-scale asymptotics. Yeah, and I guess this little z is going to be the length scale of the oscillation of the wave. Okay, so this is the length scale of the wavelength of the wave, whereas big Z is the length scale of the background variation. So we're going to do an asymptotic expansion. So we're going to have W naught and epsilon W1. And then this W naught, we are going to make this approximation where we say that there's an amplitude which depends only on the big Z, and then this rapidly varying phase. So when I wrote a paper about this, we called this approximation a specific thing, and our referee disagreed with what we called it. So I looked a little bit into the history of this approximation. So I just want to briefly give a brief digression into what you call this. So I think maybe the most descriptive way to describe this is the phase integral approximation, because that actually tells you what it is. But the first person to try doing this was Carlini in 1817, who used this to understand something that's exponentially decaying, but where the decay rate depends on space. So if you think that that's very important, you might call this like the Carlini approximation. Then in about 20 years later, Liouville and Green, it seems like this was probably done independently. They both use this approximation for wave phenomena, so where the wavelength varied with space. So that's kind of what we're going to be using here. So if you think that the describing waves is most important, you might call this like the Liouville-Green approximation. But of course, sometimes you have a region where you have waves and a region where things are exponentially decaying, and you might want to connect those. So you can try to come up with a connection formula, and that was done in the early 1900s by Rayleigh, Gans, and Jeffreys. So if that's the thing that you think is most important, you might call this the Rayleigh-Gans-Jeffreys approximation. But it's my personal belief that nothing in life is important until it's been applied to quantum mechanics, and Wenzel, Kramers, and Brouillon all apply this to quantum mechanics. So because of that, I call this the WKB approximation. So that's what I'm going to say going forward. WKB. So we're going to use this WKB approximation, and to lowest order, this gives you an equation for theta prime, which is like the vertical wave number, and that's going to be a function of z because this n is a function of z. So you can see it's a quadratic in theta prime because there's one theta prime here and another theta prime, or there's one theta prime squared here and another theta prime squared here. So you can solve for that, and basically you're going to get some interesting behavior when the discriminant of the quadratic is equal to 0, which is in this at this position here, where here so VA is the Elfing velocity, and that's related to the magnetic field strength. It's linearly proportional to the magnetic field strength, and basically you're interested in is there a height z where this buoyancy frequency satisfies this equation here. All the other terms are constants. So another thing that you can do is just plot what are the four roots of this equation as a function of height. So here I'm plotting for the specific simulation that I ran. If you change any of the parameters, it's going to shift around a little bit. But basically, if you're high up, you have four real solutions for theta prime, which is like the vertical wavelength. And those correspond to downward propagating internal gravity waves, upward propagating internal gravity waves, and then upward and downward propagating magnetic waves. Then the discriminant of your quadratic equation is 0 at this dashed line, and then below that you get evanescent waves. So in that case, you can pick the real part of the wave is either this positive number or this negative number. So I mean, there's some oscillation associated with the exponential decay, and then you also get to pick the imaginary part shown here in red. So that tells you if you're decaying or you're growing exponentially. So the big question is, what happens at this dashed line? So in order to do that, it's easiest to non-dimensionalize the problem. So it's a bit simpler. So if you non-dimensionalize, you get an equation that looks like this. The discriminant is equal to 0 when c, which is the only thing which depends on that big z, goes through 0. So I mean, on this equation, you can just use your WKB analysis. To lowest order, you get this equation. So that's what I plotted on the previous slide. But I guess what's nice is that, I mean, you can also do WKB to the next order, and then that gives you an equation for the amplitude. Now, I want to point out that normally, if you're using like the WKB approximation for, say, like quantum mechanics for the Schrödinger equation, you get turning points when theta prime goes to 0. So in particular, the amplitude diverges when theta prime goes to 0. The interesting thing about this problem is that nowhere does theta prime ever go to 0. The interesting thing is when z is equal to 0, that theta prime actually goes to 1. But it turns out that if you go to next to leading order in the WKB approximation or in your asymptotic series, you get an equation for the amplitude. And you can see that the amplitude goes like 1 over square root of theta prime. So if theta prime went to 0, there would be a turning point there. But you can see it also diverges when theta prime goes to 1. Okay, so then that tells you that you need to get some inner solution because you have this problem when theta prime is equal to 1. So physically what's going on is that there's 4 modes. We know that the mode that we sent down was an internal gravity wave. And the question is, what's the mode that comes back up? Is it going to be an internal gravity wave, or is it going to be a magnetic wave? Well, what you can do is that near the 0 of c, you can assume that c is just proportional to z. And then you're left with this equation here. So this is in some sense like the exact equation that we're solving in this inner region. And the problem is that we can't use the WKB analysis. We can't use WKB anymore. However, you can solve this this equation exactly by writing it as this integral here, where this capital theta is this phase function, which depends on the wave number k and z. And now this is an integral now in the complex plane, and you have to decide how to pick your contour correctly. And you can evaluate this, you can approximate this integral using a steepest descent. So the way to do this is that you look below the point where z is equal to 0, and you draw the steepest descent lines, and then these are the saddle points, these dots. And what you find is that you get I guess the physically meaningful solution. So that's the one that that is related to the downward going internal gravity wave and also is decaying as you move downwards. That's associated with this saddle point, and you get that if you start off in this sector in k space and you end up in this sector in k space. Okay, so we know that that this contour has to connect these two sectors, and we know that by looking at the low values of z. But if you look at z above z is equal to 0, you still need to connect those two sectors. But the steepest descent lines are different in that case. So the way that you get from this sector to this sector is that you have to pass through this saddle point and go up here, and then you can go from there through this saddle point up to here. And that means that you get contributions from both saddle points. And it turns out that this saddle point corresponds to the downward going internal gravity wave. So that's the one that we wanted. And then this one corresponds to the upward going magnetic wave. And it turns out that the amplitudes are the same, but you get a pi/2 phase shift because the angle of these two curves are different. So this is saying that basically the prediction is that if you send down an internal gravity wave, what's going to come up is a magnetic wave with the same amplitude but a pi/2 phase shift. Okay, so you could have kind of like guessed that from this diagram, because you can see that if you send down an internal gravity wave, something funny happens at this position. Something has to come back up, and your only choice is either an upward going magnetic wave or an upward going gravity wave. But the upward going gravity wave has a theta prime which is negative, whereas here it's positive. And so why is this the case? Well, it's all because of the thing that I told you at the beginning. For these internal gravity waves, the phase velocity is perpendicular to the group velocity. If the wave is going downward, the group velocity is downward. But because it's perpendicular, the phase velocity is actually going upwards. That's the reason why the vertical wave number, theta prime, is positive for the internal gravity wave. And because of that, it kind of like connects onto this magnetic wave, which is going upwards. So we can test this in the simulations. So this is just a snapshot of the vertical velocity in the simulations at one specific time. And if you just zoom into this region, you can ask, what would it look like if you had a downward going internal gravity wave, an upward going magnetic wave, equal amplitude, phase difference of pi/2, and then you get this dashed blue curve, which matches up very nicely. So to summarize, in this specific case, we found that you have wave conversion. The wave, a downward going internal gravity wave gets converted into an upward going magnetic wave at this special point where the buoyancy frequency is exactly right. Okay, so that's so that's what happens if you have a constant magnetic field. But this doesn't address the question of why do we not see things at the surface. So I don't have too much time left, so I'm just going to quickly outline how we solve this problem with a variable magnetic field but a constant buoyancy frequency. So the magnetic field that we picked looks like this. So it's a sinusoidal in the x direction, and then in the z direction, it's decaying exponentially. And we picked this so that the current associated with this was 0. So I'm just going to show you the simulation that you get from this. It's set up in the same way as before. So you send down waves, but now you can see that the waves start to develop some interesting horizontal structure. And some of the waves seem to get amplified down here, and then other waves are amplified up here. So I'm going to skip ahead. If you let this simulation run for a while, you can see that there's some really interesting features which develop. In particular, kind of the energy seems to be focused in at special horizontal locations. So is there any way that we can try to describe this problem analytically? Well, what we did was that we rewrote the equations in terms of a stream function psi, and then you can write the linear equations in this form. So this is now a fourth order equation in z for psi, but then it also has x derivatives in it as well, because now the background fields, the background magnetic field is also a function of x. So this is pretty complicated, but it turns out that kind of to lowest order, if you make the appropriate approximations, all these terms cancel out, and you're just left with these three terms up here. So for those three terms, we're going to do a WKB analysis, but the key thing is that we're only doing WKB in the vertical direction, not in the horizontal direction. And that's because the horizontal variation is supposed to be on a similar length scale as the scale of the wave. So, so to lowest order, you're left with this equation here. So now the vertical derivatives have been replaced with theta primes, but we still have the horizontal derivative. So this is a second order equation in x, where the parameters of the equation depend on z. So both the alphane velocity, the strength of the magnetic field, that's decreasing exponentially with height. And then also, presumably, these theta primes would also be a function of height. So at this stage, and we have a second order a differential equation in x. I wasn't really quite sure what to do, so I just put this into Mathematica, and it told me that the answer was Mathieu functions. Okay, so the solution is Mathieu function, which has these two parameters a and q, and it's a function of kb times x. Kb is the length scale of the magnetic field. So, so at this stage, I read up about Mathieu functions. So I became an expert on Mathieu functions. As I said, you have these two parameters a and q, which are related to the terms in the equations. So for me, these are what what a and q are. And it doesn't matter exactly what they are, but the key thing is that in general, the Mathieu functions are not periodic in X. However, for our problem, we want them to be periodic. And the condition for them to be periodic is that the a and q have to satisfy a specific relation, namely that a has to be a so-called Mathieu characteristic value, which is a function of r and q, where r is the ratio of the horizontal wave number of the wave to the wave number of the magnetic field. So it turns out that this then gives you the dispersion relationship for our problem. And if you just plot what that is, you get a plot that looks like this. So so up here, where the magnetic field is weak, remember magnetic field goes like e to minus z. So up here, the magnetic field is weak. All you get are the internal gravity waves. And for that, you're basically just left with the internal gravity wave dispersion relationship, which is that the vertical wave number would be constant in this case. However, as you move downwards, the magnetic field becomes stronger and stronger. And then it actually depends if the wave is in phase with the magnetic field or out of phase. And depending on if it's in or out of phase, you get these different curves up here. So there's actually two curves here. The blue curves, there's two of them, but they line up with each other because there the magnetic field is weak. It doesn't do anything. The two polarizations give the same vertical wave number, but then once you go in this region, so if you're at large wave numbers, then it does make a difference. So so I'm not going to go through all the analysis because we're running low on time, but basically what we found is the same thing as before, that if you send down an internal gravity wave, it's going to convert into a magnetic wave with the same amplitude and a negative pi over 2, or with a pi over 2 phase shift. So I'm going to skip how we got that. So once you have all that, I mean, that gives you some theory, and you can compare that to the simulation. So this is kind of what the theory is. Oh, sorry. I guess there's one thing, something very important that I want to point out, which is that it turns out that these vertical wave numbers, the theta prime, actually diverges at a finite height. So that's what I've shown in these purple curves here. Okay, so you get some theory. You can compare that to the simulations. I mean, if you kind of compare these two, in many respects, they look very similar, but it's not quite as good as in the constant magnetic field case. In particular, in the simulations, we get these vertical oscillations near these special points x equals 1.5 and 4.5. That's where the magnetic field goes to 0. And there's some behavior there that goes on in the simulations that is not present in the theory, that we don't really understand. If you take kind of like vertical slices through that, again, you can see that the agreement is very good, except that here you get all these oscillations. So I'd say that's kind of like the last thing that we don't really understand. Why do you get the oscillations in the simulations? Is this like from some higher order term in the equations that we neglected? Is it some sort of like numerical dissipation? As far as we can tell, it's not, but it seems like maybe you need to regularize the problem on some higher order to figure out what's really going on. But of course, I mean, in the stars, there really is some dissipation. So in a star, we think that as these waves kind of focus in, that they would probably end up dissipating. And that's the reason why you would not see them at the surface. So in this case as well, we find that you have this wave conversion, and that's again because the internal gravity waves have a phase velocity perpendicular to the group velocity. The downward going wave has a positive wave number. So I just want to just briefly state that the next thing that we want to do with this is to do the problem in spherical geometry. So we now have this new spherical version of the Daedalus code. And this is an example of a simulation that was run by Evan Anders, postdoc at Northwestern, where you have convection in the interior of a simulation, which is generating waves, internal gravity waves in the exterior. So that's like the opposite of what's going on in this problem, but it's just like illustrates how, like an illustration of how the code works. Okay, so I think that I've used up my time. So I guess these are my conclusions. Again, I just want to emphasize that that for internal gravity waves, the phase velocity is perpendicular to the group velocity. That means that if you have a strong magnetic field in the core of a star, you send in an internal gravity wave, it's going to be converted to a magnetic wave. The magnetic wave is then going to damp because as it propagates outwards, because the magnetic field decreases in amplitude. So, and that happens again because group velocity perpendicular to phase velocity for the internal gravity waves, and that's what I wanted to tell you guys about. So, thank you.